All right, so we are now moving into another area of chemistry, but maintaining the same understanding that we're using mole concept. We're using stoichiometry. We're using the idea that we're utilizing these understanding of these free particles to mean something. We're really doing chemistry because we can predict outcomes now once we understand we have a chemical formula and the ratio of either the ions or the atoms that create that. All right, so I'm going to do a demonstration here that I hope kind of links to what we're talking about. Talk about solubility, right? And we talk about using our solubility rules or our table, okay? And if we look at our table for solubility, we see that hydroxides, okay, are normally insoluble. We talked about Coulomb's law. We're not getting away from anything that we've already learned. We're just kind of adding a layer onto our understanding and then expanding our zone. We talked about redox reactions, a lot of reactions. Most reactions are redox reactions. Now we're getting into acid and base chemistry that uses the same understanding of mole ratios and stoichiometry and adding and understanding the ratios of, let's say, in this case, hydroxides to protons. So we're adding now another level of chemistry, but we're maintaining what we know. So hydroxides from Coulomb's law. Okay, we know that oxygen and hydrogen are very small. And being -1 in a small area by Coulomb's laws means that there's a high electrostatic attraction. And because of that high electrostatic attraction, okay, hydroxides are normally insoluble. Okay, so we know that. All right, and there it is. Now there are some exceptions to that rule. Okay, if that really -1 in a small area, I like to call electron density. So if you have that -1 in a small area, can attract something pretty positive, that's going to be hard for water, which isn't a total positive or negative, it's a partial positive or negative, okay, to compete for and break those ions up and dissolve them. So most hydroxides are insoluble. There is some exception. In the group 1 ions, because they're big atoms to begin with, yes, when they lose an electron and become positive, they get smaller, but they start out pretty big, they're just +1. And being +1 over a generally relatively big area makes it hard for the hydroxide. But once you start getting +2s and +3s that hydroxide has, okay, and because it's small to begin with, okay, it makes insoluble compounds. And so I'm talking about something we've already talked about, Coulomb's law and solubility. So I'm going to start with something you probably have used or seen in your medicine cabinet, milk of magnesia. Okay, milk of magnesia is a salt, okay? And if you look at its chemical form, if you can read that, what's that say? Anyone?
Magnesium hydroxide.
Yes, boys and girls, very good. So yes, magnesium hydroxide. You guys did that in unison. All right. Not a reading lesson, but you did an awesome job. I can barely see that, but how you did that. So magnesium hydroxide. And so from our basic chemistry skills, we know that magnesium, okay, Mg, we know that it's right here. It's got 2 valence electrons. Everything in this group, the second row, loves to lose 2 electrons. We know a hydroxide is -1. So the formula here is going to make this thing compound neutral. We always write neutral compounds is MgOH2. Okay? OMG, no. Okay, MgOH2. That's your new text thing. So, okay, forget the OMG anymore. If you're really, really cool, okay, just like we say mole without the E, we say MgOH2, all right? Maybe not. Okay. I geeked out on you there. The point is, that's magnesium hydroxide. And of course, based on our solubility rules, it's not one of the exceptions. Notice calcium +2, barium +2, strontium +2. Those are soluble. Why do we know as we go down? What happens to the size of the radius? Right, so even though +2 you lose 2 electrons, the +2 ion gets bigger. You start stretching that +2 over a what? Larger area, and so calcium, barium, strontium, even though they're still +2, they're bigger +2s. Those +2s over a bigger area, Coulomb's law, right? That -1 hydroxide can't really attract it too well, so it dissolves. But magnesium, okay, is still small enough. It's a third row element that it's still, because of Coulomb's law, too attractive. So magnesium hydroxide doesn't really dissolve. So I'm not going to pour from a bottle. I'm going to take, okay, good old-fashioned magnesium hydroxide, and I would never do this if I wanted to take this. Remember, magnesium hydroxide or milk of magnesia is an antacid, okay, which means is, for whatever reason, you're producing too much acid, you are have a lot of anxiety, maybe you have a weakness in the lining of your stomach. Remember, the parietal cells make hydrochloric acid, so that's pretty corrosive to tissues, as I'll talk about. So, for whatever reason, you might have taken antacid, and we'll talk about them. So, Tums, milk of magnesia, Rolaids, these are all bases that can neutralize the effect of acids. We'll talk more about that, but here is milk of magnesia. Notice it's a solid. Okay? And it's not going to dissolve well. So when I put water with this, okay, it's not going to dissolve. It's going to look like, essentially a lot like what?
Milk.
Milk. And by the way, milk is a colloid. Milk is not a solution. Milk is essentially a mixture of many different compounds that don't actually dissolve. So milk, even though it takes a long time for it to settle, it's a colloid. So it looks a lot like milk, okay? So that's exactly, if you were to pour out milk of magnesia, look into the bottle, that's what you have. And the reason why you can't see through it is why? The solids aren't really what? Dissolved. And that +2 ion and that hydroxide ion attract themselves too much. Water can't compete for those charges and surround the ions, so this stays undissolved. And there's a good reason for that, because we know that milk of magnesia is really a pretty strong base, relatively, if it's activated. Now, in truth, in chemistry, we call this a weak base, okay? Because in solution, there's barely any hydroxides. We'll talk about this. So this base has all of its hydroxides locked up into the solid. And that's a good thing, because when I drink this, and I'm not going to drink this, okay, but if I was to drink this, because I have an acidic stomach, I don't want the action of the strong base or the hydroxide, let's say ion in the salt, to interact with my esophagus. I don't want to wear that away. So it's pretty interesting. So this is pretty safe to drink. And I'm going to say to you right now, hydroxides are dangerous. OH minuses are dangerous. Does anyone know where we use them in our household? If I have a high concentration of free hydroxide ions, okay? Anyone use that in your household? Drano. Drano dissolves hairballs or whatever stuffing your pipes in your bathrooms, okay? Over time, because of shaving and or clipping hair or whatever human things get stuck in the drains, Drano can dissolve organic compounds. Hydroxides are caustic. We're drinking hydroxides, OH minuses. And you may say, well, why are OH minuses dangerous? OH minuses, when you think about it, if they're in high concentrations, okay, can dissolve organic matter. Here's the reasoning. Here's an oxygen. It has 1, 2, 3, 4, 5, and 6 valence electrons. You should know that in our chemistry. Hydrogen has 1 valence electron. Now we know in our basic Lewis dot diagrams, oxygen wants to have 8. Here's oxygen. It needs 2 more electrons to share to get what? Stable. So somehow, some way, this thing absorbs an electron from its environment. I'll draw that as an X. This whole thing now becomes a polyatomic ion. So what you have here is something with a great number of electrons. More than it, what? Is supposed to. And on top of it, it's really negative. So what happens, party people? This can attack things that are positive in nature. For instance, okay? And this goes back to biology. Remember the amino acids? Okay? Here's what an amino acid looks like if you forget. We have a carbon, double bond to an O. This is bonded to an N, to another carbon, to a carbon double bonded to an O. And this right here is the peptide bond. This is bonded to an R group. That changes the amino acid. Okay? This is bonded to an H. This would be an H. And the beat goes on. This would be a carbon bonded to an R group. This is bonded to an N. And it goes on. So this right here, party people, is a peptide bond. And if you remember, amino acids, The different types of amino acids are based upon your what? Different R groups. They're polar, non-polar. And you know that different amino acids build different proteins. Different proteins have different functions that drive chemical reactions in our body. So think with me for a second. I have a hydroxide ion, okay, that is rich in electrons. Now, think with me. Nitrogen in a periodic table is closer to oxygen. So what this nitrogen does is pull the electrons away from the carbon. Hey, look where oxygen is. Oxygen is where? Even more electronegative than nitrogen, right? That's what we call oxidation, right? So this oxygen pulls electrons even farther. So what we've done is we've taken the electrons kind of what? Away from this carbon. So this carbon is kind of positive. So what this guy does is attack this carbon, okay, gives it an electron, and this electron that was right here in this bond gets pushed over here. And that bond is broken. Okay, I don't care if you don't quite understand, it's called a mechanism. So hydroxides with their extra electrons, okay, find something positive and there's in between the carbon and nitrogen, okay, it's going to find the carbon positive, and why? Because these guys are pulling it away. So this electron bonds here, pushes this bond away, you break this amino acid, okay? And that's pretty darn dangerous to be breaking proteins. And there's other things it breaks. The proteins in your hair it breaks down, okay? So OH minus are very caustic. But this isn't, okay? Drano, is because it's what? Free hydroxide ions. This isn't. These hydroxides are locked in a what? Solid crystal, so not dangerous to us, not caustic, is not going to ruin our esophagus, okay? So this is insoluble, and this is where we left off, right? Precipitates, but I'm not telling the entire story. This can become soluble. How? Well, because it's a salt that has a what? Mg plus 2, and a what? Hydroxide negative. And I'm just going to draw this simple structure, simple cubic cell like this. It's not really this way because it's a 1-to-2 ratio, but I'm just drawing it for simplistic cases. This hydroxide ion is exposed on the corners, right, somewhere? And it loves what? To attract something that is positive. So party people, if an acid, which you should know is something that delivers an H+, okay, a proton, and we know that when you deliver an H+, you're an acid. We'll talk about the definitions, but the easiest definition is the Arrhenius definition. You deliver an H+. Classic example, hydrochloric acid. Gives off a what? H+, and what's remaining is a Cl negative. So if I have H pluses in my stomach, guess what? Parietal cells make hydrochloric acid. So what happens is this H+, hey, what is an H+? Isn't that a hydrogen atom? And a hydrogen atom has what? Atomic number 1, mass of 1. Let's go through this. How many protons does hydrogen have? 1 proton. If it's an atom, I say atom, you say? So how many electrons? Right, so the whole thing is neutral, right? 1 electron, 1 proton. Now, when it becomes H+, it loses a what? So all it is a what? A proton. A proton is a piece of a nucleus of an atom. Talk about Coulomb's law. I'm not even an atom anymore. I'm a what? A fraction of an atom. So I'm +1 in a very small area. What do you think the Coulombic attractions for H+ are? Right, and you may say, well, why are acids dangerous? Hydroxides are dangerous because they push an electron to break bonds. What do you think a proton does? It pulls electrons. Every bond here is a pair of electrons. So H pluses will suck electrons away from bonds and break them down. That's why they're dangerous as well. Now, we have mucus, okay, and we have a way to defend against that in our stomach. Okay, because we use the hydrochloric acid to break down things. But if I deliver acid, okay, to the milk of magnesia, magnesium hydroxide, this guy's a heat-sinking missile for something negative. Who's negative? Who's got extra electrons to give? Right, so an OH minus and an H plus is going to make what? H2O. And H2O is not going to stay in that crystal. Why? More than water. What's its charge? 0. It has no charge, so why would it stay in the crystal? And my friends in chemistry, this is neutralization. Neutralization, we took a dangerous H+, who is a heat-sinking missile for electrons, which, by the way, will pull electrons from metals. How did I make the hydrogen balloons that exploded in class? I dropped hydrochloric acid on zinc. Zinc gave up its electrons willingly to the H+. H+, got electrons, they became hydrogen. Okay? Now, let's do that. So, this is insoluble, correct? In water. But what if I drop some acid on it? And yes, I'm dropping acid today in class. Okay, now I'm going to use a concentrated form of acid, which I have back here. So let's drop some acid on the magnesium hydroxide. All right? I hope you can see my segue. We're not moving into a different chapter. Yeah, we are. We're using our same skill set, okay, using deeper understanding. So, I'm dropping H pluses and chloride ions. Let that rock.
Oh, man.
Oh, woman. Okay. And so, given some time, if the H pluses are pulling the hydroxides and making water and pulling them out of the crystal, what should I see eventually? Should I be able to see through this? Absolutely. Okay? And so magnesium hydroxide becomes soluble in an acidic solution because it's got the hydroxide because of the acid-base reaction. Okay? And look at here. Okay? You're starting to be able to see through me. Okay? It's getting clear because I'm taking away the precipitate. Okay? I'm dissolving the precipitate because of the action of the acid onto the hydroxide. This is what happens in your stomach. It's safe in your esophagus. You don't break any bonds. Now, would Drano work for your stomach? Yes, it would. Drano would do the same thing. But you would wind up burning and probably perforating your esophagus because of the delivery of the soluble hydroxides. This is beautiful. It's insoluble. Therefore, in the water solution, it has no effect on our bonds. It doesn't break any bonds, the hydroxide, until it hits the what? Acid. And this is the beauty part. Now we can do stoichiometry. That reaction, was that a completion reaction? You bet your donkey. Okay? Now, if you've got a donkey, you could also call your donkey. Okay, but the point is this. That is now a driven reaction. That's a completion reaction. Could I figure out who the limiting reagent is? Okay, by looking at that, who do you think the limiting reagent was? The magnesium hydroxide was limiting. That reaction stopped once of what? All the acid did this to it, of all the hydroxides, correct? I probably added excess what? Acid. So this is a limiting reagent problem. This is a driven reaction. Everything we can do this. So anytime I drive a reaction, and I always drive what we call a weak base. Magnesium hydroxide is a weak base because by itself it doesn't what? Dissociate. Strong bases. What are strong bases? Okay, what are soluble hydroxides based on table foo-foo? What are soluble based on table foo-foo? Let's look at it. Because you've got to know who your strong bases are. Why? Because if I've got a strong base or a weak base, I can drive the reaction stoichiometrically. So look at hydroxides. Normally they're insoluble. If they're insoluble, if the compound is insoluble with a hydroxide, that is a weak base. That means in water, it doesn't break apart into free hydroxides enough to make the solution basic. Basicity is about this hydroxide ion being free in solution. So because magnesium melted magnesium, magnesium hydroxide, does not dissolve in water very well for reasons I just explained ad nauseum. Solubility, Coulomb's law, it is a weak base. How about copper hydroxide? How about copper hydroxide? Is copper hydroxide, copper 2 hydroxide, is that a strong base? Is it soluble? Is it one of the what? The exceptions. Is copper here as an exception? No. So copper hydroxide is a what? Weak base. How about zinc hydroxide? Weak. Okay. How about aluminum hydroxide? Weak. How about sodium hydroxide? Anything that's a group 1 ion. So sodium, potassium, rubidium, cesium hydroxide. Why is it strong? Because it completely does what? And makes free hydroxides. Okay? How about calcium hydroxide? Yes. How about barium hydroxide? How about strontium hydroxide? Yes. Now, there is a little issue with these guys right here. These guys right here, they're only completely dissolved in low concentrations. They have an issue because their charge is a little higher. So after higher concentrations, they become insoluble. So they're completely soluble, okay, but only in low concentration. So once you start getting a little higher, the positives, that positive 2 causes an issue. How about ammonia hydroxide? Strong, very good. All right, let's take this down. Now, if you are a strong acid or a strong base, you are called an electrolyte. Okay? What does a base do? Bases provide somehow free hydroxide ions, which in high concentrations are dangerous. Yes? This bottle's leaking? Maybe. Thank you. Oh no, it's this darn can. Okay, that's not good.
That can of Drano.
Yeah.
That's not.
Right.
Just what we were talking about.
Let me just slip that.
Okay, so
They on some weird shit.
Wait, what do you say?
so we got Drano with free hydroxide ions. Watch out for those ions there. Okay, of course that doesn't work. Those are.
That's what that does. Oh.
Okay, so what else is an electrolyte, you think? Electrolytes are anything that has a great number of ions in solution. And the reason why we call it an electrolyte is if I've got a lot of ions in solution, then those ions are free to conduct electricity. Okay? So, let's do a little test. So you're going to hear the word electrolyte more so in the regions part of this course, but the AP card, we don't do a lot with this, but you need to understand how this works. First of all, strong bases that completely dissolve and produce hydroxides are electrolytes. Also, these are my bases, right? Acids. We know bases are dangerous because they bring what? Extra electrons into a bond and push them out. What's an acid? Something that delivers what? H pluses, the other word I use is protons, okay? And these guys are dangerous because they take electrons from bond, okay, a little differently. These guys will push them out, these guys will take them. That's why they're dangerous for organic things that share electrons. Now, what's an electrolyte? Well, an electrolyte is something that conducts electricity in solution. So what I have here is I have Ernie, the light bulb, okay? And Ernie the light bulb, I powered the, this is plugged in. I close the circuit, Ernie should light up. Ernie, okay? Now, the reason why this is working is I have metals. Metals have what? Mobile electrons. We've talked about metallic bonding, right? So these electrons are able to move throughout this entire crystal. This, what? Face-centered crystal, what? Simple cubic structure. Electrons are able to be mobile because they're loosely held. So mobile electrons in what? Metallic bonding cause what? Conduction electricity. For those that don't understand or forgot, here is a metallic bond. You have your nuclei. This could be, in this case, I'm using aluminum. Now the electrons are free to what? Move throughout the entire crystal because they're loosely held. So they kind of move through all of what? The nuclei. Now, if I've got a negative, a negative, and a negative, if I put a big negative here, that's going to repel that one, isn't it? That's going to repel this one and move this one to what? The other side. And that negative, of course, gets to the other side. It's not perfect. It's not a superconductor. There's going to be some little bit of loss of charge because you're moving a little bit of mass, right? So there's a little bit, okay? And some things are better conductors of others. But that's how it works. Now, if I have nonmetals, nonmetals hold on to electrons what? Me and Curtis have a firm handshake. Okay? Firm handshake. We're a covalent bond. He wants this electron, I want it. So our bond is so local right here that you give us a stress, we're going to break. So because we're fighting for electrons in our bonds, these electrons aren't free to move. So if I've got nonmetals, like which is the insulation around wire, those electrons aren't free to move. So therefore, if the first one can't move, the second one can't what? Repel the other. There is no mobile electrons in things that are made of nonmetals. But that's not what we're talking about here. We're talking about solutions. So, first step. Okay, let's unplug this so I don't charge myself. Okay, so I've got my two metals. And now I'm going to take Vasa, pure water. Okay? People think pure water is an electrolyte. Okay, it's distilled water. We boiled off the water. This is no ions in this one. In truth, there probably is some ions. It's not deionized. But if I put pure water, Ernie doesn't light up. Water does not, by itself, conduct electricity. What conducts electricity? Movement of ions that are free or movement of free electrons. What's water? Hydrogen, a nonmetal, who's small and pulls on them. Oxygen, a nonmetal. Nonmetals molecules don't conduct electricity because their electrons are being held tightly. So water is not an electrolyte. Water does not break apart into ions that much. We'll talk about that more tomorrow. Now, interesting enough, let's talk about a type of salt. There's many types. We dealt with magnesium hydroxide. Here is table salt. Okay, so table salt. All right. Now, table salt, we know forever, begin this course, is Na plus Cl negative, repeating in this arrangement. So here's table salt. It's made of a metal. Metals have electrons, right? So if I put these electrodes in here, I should get the light bulb lighting up. But remember, to conduct electricity, what do I need? Free mobile electrons. Hey, if I'm a plus or a negative, wasn't there exchange of electron? Wasn't there a redox reaction for me to go with Na0 to Na plus? Cl0 to Cl negative? There's already an exchange of electrons. There's no free electrons anymore. And these ions in a crystal, are they mobile? They can't. They're stuck by electrostatic attractions. But if it's soluble, and Na plus is +1, Cl negative is -1. Those are weak electrostatic attractions. If I add water to this, if I add water, what's the water going to do?
It's going to break it up. Break up the part.
It's going to do what as I dissolve this? At some point, these guys should dissolve. Now, it would be helpful if I plug it in. So let's go back to water. Let's do this again because I really blew this up. Okay, let's start with pure solid because it was never going to work without being plugged in. Okay, so here's our salt. Okay, it's not going to, no, just to show that it's on. Christmas in July. Here we go. Two metals, free moving electrons. Stick it in the what? Right, now, I'm going to add some Vasa. And we have conductation. Now, I'm not touching them. Okay? So what's making that light up? The free ions moving. Now, if you don't understand how that's working, I'm kind of cheating there. But if you don't understand how that's working, is what's happening. If I've got free ions. Here's a plus, here's a negative, here's a plus, here's a negative. I put something negative right here in my solution. Who's going to come running? The positives come running. And the negatives will probably repel. Over time, what are you going to have? All the positives where? And where over here? Didn't we make this side of the beaker negative? That's how conduction of charge works, as long as the ions are free. Ionic compounds conduct only if you dissolve them if they're soluble, and or if we melt them. That's when they're electrolytes. So who's an electrolyte? Salts, but only when what? When they're dissolved in water, if they're soluble, free ions, or if I heat them enough to melt them. I don't have enough heat to do that here. Good. Oh, who else makes free ions? Who else makes free ions? Who else makes free ions? Okay, well, let's take off, let's look at some Vinegar, as we say in West Hampton, as I learned. I would like a Vinegar bagel, please. So let's look at some Vinegar. Vinegar, if you haven't already noticed, vinegar is an acid. It's a weak organic acid. So what does it produce in solution? Theoretically, free what? Now it's a weak acid, so it produces a lot of H pluses or a little bit? Little bit. It's a weak acid. Now what's vinegar look like? Okay, we'll learn about this, but vinegar has this formula. It's a carbon, double bond, and to the O. It's really cool. It's a weak acid. Why? See these oxygens? They pull on this pair of electrons this way and expose what's left. An H plus, right? So my friends in chemistry, but it's not a great acid, but it does give off some. So it's a weak acid. Now the reason why it's bright is because two metals touch. So weak acid, but it's an electrolyte. You with me? Now what if I have something that gives off a lot more? Here's hydrochloric acid. We call this a strong acid. Now, weak acids do not give off every single H plus possible. This is a good system of pulling some H's, but it's not great. Okay? So most of the acid actually barely goes undissociated. In fact, vinegar is only 5% undissociated. So 95% of it remains like this. So it gives off a little bit of H pluses. So it's an electrolyte because it makes free ions, right? But it's not a strong electrolyte. Now if I start with hydrochloric acid, okay, and where's my hydrochloric acid bottle that I had? It was a clear bottle. I was pouring for the magnesium. Good times. I need help most of the time. Okay, well, we'll try this one. Here's hydrochloric acid here. Okay, so hydrochloric acid completely breaks apart. Stoichiometrically breaks apart. What does that mean? Every single HCl breaks apart. So would you say it's a stronger or weaker electrolyte? Right, there's more free what? Right, so there is that. And where did I do with the Vinegar? I just moved it.
It's right
there.
to the left hand.
Yeah.
Not that.
So there's that, there's acid, and this is the Vinegar. Now, my light bulb that's not a strong acidic solution, so let's make it stronger. Okay, I kind of have a diluted HCl, but HCl has the potential, okay, to be up. Now, where is my, I put it somewhere. All right, so stay with me. All right, so I'm going to pour some concentrated hydrochloric acid, which means I'm going to need some glasses. Okay, so here we go. This is concentrated. Now, I gave you concentrated Vinegar. Oh yeah. Okay, so this is a Vinegar. Weak. This is basically regular vinegar. Now this is regular hydrochloric acid, but just less water mixed with it. Who's a better electrolyte? Hydrochloric acid. Why? It has more what? Right. This stoichiometrically breaks apart. Vinegar stoichiometrically breaks apart? No, because it doesn't all what? Which one's a completion reaction? Okay, good. Now, one more thing. Let's look at sucrose. Sucrose. Now, what's happening is the hydrochloric acid is reacting with the aluminum to make hydrogen gas. Okay, so it's also doing another reaction. Remember. Now, here's sucrose, which is really what? Sucrose, party people, is table sugar made of glucose and fructose. It's a molecule made of what? Carbon, hydrogen, and what? Are these metals or nonmetals? And nonmetals do what with electrons? Keep them tightly, right? So if I put this in a solid of sugar, which is a disaccharide, okay, is there any conductivity? No. Okay? And so I had these molecules up when you walked in. Gosh knows what I did with them. Oh, right here, maybe? Yeah. So look. Here's, what are these guys made up of? This is a carbon here. These guys do what with electrons? They share them? They share them between bonds, but they're holding on what? Tightly. There's no free what moving around. Right, okay. But let's add some water. Because this is polar, right? See the oxygens? It will H bond with water, right? We talked about that. So it's going to dissolve. But sugar, like water itself, doesn't break apart into ions. It's not made of ions. So I can dissolve sugar all day long. It doesn't conduct electricity. Pure water doesn't conduct electricity because it doesn't break apart into ions. And when these guys touch in the water, they do. The truth is they break apart a little bit in ions. And don't do this, if I was to jump into pure distilled water with no ions and drop a toaster, and if I was myself clean, I wouldn't get electrocuted. The problem is, naturally in my body, I produce ions and urea, so that wouldn't work. So water by itself doesn't conduct a charge. Who are electrolytes? Who creates free ions? What's that? Metals? Metals not. Metals conduct electricity, right? Because of free moving what? Electrons. Acids, bases, and soluble salts. Last demo here. Let's go liquid Drano that I messed up here. Liquid Drano is eaten through the can. Liquid Drano is concentrated hydroxide. So liquid Drano, do you think does it have a lot of ions? It should. It should. A little bit. Okay. See you tomorrow. I'll post what's homework.